So hello, I'm Jason Mancuso. I work for a company called Dropout Labs. We work on secure and privacy-preserving machine learning. I'm also the organizer of the Cleveland AI group. We do stuff like this, but also educational study groups and social events now. Happening roughly once a month. The study group is happening every other week. It's at ThinkBox. We're going through Fast AI, which is a Python-based introduction to deep learning. And if you're interested in that, definitely connect. Actually, the first one was last week, but it was just like a setup. So there's like still time to get caught up if you're interested in that. But next Wednesday is like the first one where we go through the first lesson, which is actually we're expecting people to have watched the video and gone through the course and everything, or the first homework assignment, which each takes a couple hours a month or a week, but or every 2 weeks now. But anyways, if you're interested in that, just let me know and we can talk more about it. This was a talk that I gave at ODSC East in Boston, but has been given a couple times before in different flavors and variations. My coworker Jan is not with me today, but he helped prepare these slides as well. So what we're going to talk about is privacy-preserving machine learning in TensorFlow with TF Encrypted. That's the title, but really I just want to talk about like what privacy-preserving machine learning is, what it means, the technologies that we need to be able to do it, and all the different ways, like essentially looking at like the two major ways we do machine learning, which is like the training phase and the deployment phase, how that gets a lot more complicated when you throw privacy into the mix. So first, why do we care about privacy in machine learning? And actually, we don't really approach this from like a consumer privacy perspective as much as a bottleneck perspective. So in like the current machine learning process, it's a pretty standard process now, where you have some data set that you've collected, you go through training, and then you deploy it in a prediction service. And so the data can come from a lot of different places. It could be a public data set that you found online, like ImageNet. It could be provided by a single person or something like this, like a doctor, or it can be provided by a corporation who wants to sell that data to you so that you can use it for your machine learning model. But the problem here is that getting access isn't always easy in these cases. And then at the end, after you've used the data set that you've gotten, trained the machine learning model with it, you then want to deploy it in some kind of service for prediction, whether that's to external clients or internal clients within some organization. Here, this is pictured as an external client, but it doesn't necessarily need to be a guy with a phone. And just to motivate why we care, in particular, I guess we'll use this running example of skin cancer image classification. So a few years back, researchers from Stanford published a paper that claimed to have expert level skin cancer diagnosis using deep learning. And this was something that they wrapped up into a mobile phone application where you could do this on your phone, essentially take a picture of your skin lesion, send it to a server. That server had a deep learning model on it that would process the image and tell you whether or not you should go see a doctor or not, like whether they're sufficiently confident that it wasn't cancer, or whether it flags it as cancer, in which case you're not entirely sure, but you recommend that an expert see it. This is great because now a process that takes a long time, that requires a lot of money and skill, can be done automatically beforehand to A, lower the cost of the service, and B, free up the doctor's time, right? This allows hospitals to like kind of streamline how they deal with this. And not only that, the service can be deployed and touch millions of users, where a single hospital can't necessarily touch all of those users that this application could. So obviously, machine learning is positioned to have a huge impact on healthcare, but the scalability, which is like the core of why this is interesting, I would say, applies to basically any industry. And hopefully, I don't have to sell everyone here on the impact of machine learning on a variety of applications. But so essentially they followed this process to create this application, but now when we talk about, especially healthcare, we want to look at potential bottlenecks that show up in this process. So the first is data access. So in the case of, for example, the doctor who gives up their skin cancer data set to train this model, there's liability there, right, with HIPAA. That doctor is liable then for any privacy issues that arise throughout that process, and because they're not the ones training the machine learning model, they take on a liability risk sharing data with anyone. They would have to de-identify it and go through a series of other steps to be in compliance with HIPAA. And HIPAA doesn't even guarantee that the data won't be eventually leaked, right? It does its best, but it's not perfect. And similarly, if you're a corporation and you want to sell data to someone so that they can use it for their model, you're probably not willing to do it because you don't know how they're going to use that data in the future. That data represents a significant asset. All the money that you put into collecting the data, cleaning the data, storing the data, essentially your whole team that helps create the solution, you'd essentially be giving all of that, the asset that's represented by all of that labor, you'd be giving it to someone else and trusting them with it, which in a competitive landscape is not good for a company to do. So in order for the value of this data to be offset by the person buying it, it's exorbitantly high, essentially. And so this doesn't happen as much because a lot of corporations would have to price the data so high that people who want to buy it can't. Additionally, on our side, not the data, the data access issue is more about risk on the data provider side, but on our side, the machine learning side, there's also risks that we have to do. So in case we do convince someone to give us their data, now we also assume risk by working with that data, by storing it and by processing it in plain text. Storing it we can do encrypted, but we can't necessarily process it the way we do machine learning now in some kind of encrypted state that keeps the data secure. But then on the user side, there's also incentive issues with this. So for the skin cancer example, maybe if I'm a user and I have a particularly sensitive area where this skin cancer shows up, I don't want to take a picture of that and send it to some server. Additionally, we care that if I'm going to give it my data for this process, I want the model to be accurate, right? I'm not going to do this and then get a bad result because then it's just a useless risk, I guess. Or even just it's a waste of time to use it. So, and this is kind of the problem that we see as we move things into privacy-preserving machine learning. Maintaining accuracy is extremely important, and some approaches work better than others, which is what we'll talk about. But then on the other side of that, not only does the user not want to expose their own data, but it's possible that by serving predictions at test time, you can leak information about the model as well as the data that it was trained on. One way to solve this privacy problem, data privacy problem, is just send the model to the user. That way they never have to send their data to you. You took on all the risk essentially by sending your model to them, which is okay, but then someone can then use that for whatever they want. So they can steal that model, your competitors could, or perhaps more or less likely, an adversary who gets a hold of your app can query the model, take it, download it, and then they now know exactly what model you're using in production. So they can do whatever they want with that, which means that they can potentially craft inputs that will harm the model, or they can try to attempt to control its behavior in certain situations. So, and in general, it's a bad security practice to ship out material that users don't necessarily need in order to run through the service. And so what we end up seeing is that if we can shore up some of these bottlenecks, we'll end up with a whole entire system that complies with traditional computer security principles much more. And there's a really good paper by Nicola Paperno around applying some traditional computer security principles to machine learning security, because it's a very new area, and it turns out that a lot of people doing research in the area don't come from a security background, so they don't actually they don't actually investigate it in a way that's proper in terms of security. They don't apply with realistic threat models. There's like 2,000 papers out there being published every year on adversarial examples under the guise that adversarial examples are like a problem, a security problem, when in actuality, like, they don't have a realistic threat model. If I want to, do something with a model, there are much better ways to attack it than, I guess, without knowing what adversarial examples are. This is kind of abstract, but let me just say that this is in line with traditional computer science principles or computer security principles. So one way we could do this and fix the situation, solve some of these bottlenecks, is with sanitization, or what's known as differential privacy in academic circles. And so what differential privacy does, or sanitization does, is applies a little bit of noise at each step in this process where you want to mask information. So for example, the data coming in, we don't take the data without this noise added onto it. And so the noise is carefully constructed so that we can reason rigorously and mathematically about the amount of privacy loss per individual data point, which is ultimately what matters, because a lot of times we don't care necessarily about the privacy of aggregate statistics over a data set. We care about the privacy of the individual data points. So if we do this, we can sanitize this whole process, which helps with risk management, because now we, as the model trainers, we can't actually access any of the individual data points in their original form, or at least if we do access a single point, it's going to have enough noise applied to it that it'll essentially be scrambled in a way that we can't recognize the true characteristics of the data point before this noise is applied. This also helps with leakage. It's shown that you don't necessarily, you can apply differential privacy not only to data but to models themselves, and train models in a differentially private way, so that when you query a model, you remove the leakage that happened that I mentioned before. This is all a little bit abstract, but and like the math behind it is fairly in depth. But the idea here is just applying noise to data, or to the way that you serve a prediction in a way that masks the information that you get out enough that there's a trade-off between how much noise you add and the utility you still get, the accuracy you still get, which is kind of the problem here. Doing this for the whole pipeline will not result in an accurate model, and it won't result in performant machine learning like we're used to. So we do need something else if differential privacy, so far at least, is not enough to provide privacy-preserving machine learning that we'd like. So also, as I'm talking, feel free to ask questions, because this is like a lot of information in one talk. So, and I've like more time than this talk will fill up. So definitely back and forth is good here. If anything doesn't make sense. Yeah.
Sorry, I walked in late. So
sure.
I'm kind of getting the idea that you're building a image, like you could snapshot a picture of a metal envelope, for example,
Mm-hmm.
and then you're saying, you gotta do something pre-processing to send it to you, so you don't give away your model to somebody else that might want to, because the real value of your AI is going to be the model, right? So you got to do something to the image to basically scramble it, encrypt it, or whatever, like a two-way encryption kind of model. Is that right?
Yes. So we started off a little bit broader and just said, here's the normal machine learning pipeline: provide data, train a model, serve predictions, and then talked about these different bottlenecks in the potential in this workflow. And now we're talking about like how do we improve on those bottlenecks, basically. Like, how can we set it up so that the users, the model trainers, and the data providers, the model trainers, and the users are all sufficiently incentivized to do this for essentially all use cases without caring about the privacy of the data, such that the privacy is taken care of. They can be confident that no one is going to get a hold of the data who shouldn't have access to it, and in particular, shoring up risks between these three parties. And so one way of doing that is adding noise in this way. But we're not actually going to talk about this one for the rest of the talk. We're going to talk about a different one that I'll talk about next. Sure?
Can you provide a little more insight into noise, what that is exactly?
Yeah, sorry. Noise is, I guess, you can think of noise as like a sample from a distribution.
Okay.
So you have a random distribution, you take a random sample from that,
Yeah.
as long as the way you sample that number is sufficiently strong in an information theoretic sense, you can use that as noise to mask the original data. So, for example, like an image, you can take, like an image is just, each pixel is 3 numbers between 0 and 255. For each of those pixels, I can sample a number, maybe between 0 and 10, and then add it or subtract it from the image.
Okay.
And now I've got a slightly different image, right? But instead, if I take random numbers between 0 and 255, add them, and then take the modulus, mod 255, so that I stay in the same range, now I have essentially an image that's just white noise. It's like pure randomness. But, so we'll actually get into some of why you would do this, but in differential privacy, you don't want to completely scramble the image where it's unrecognizable, but you want to scramble it enough that privacy isn't lost. And so there's like a trade-off between how much noise you apply and how much data you are pulling out of the data set. So if you're pulling out a lot of data, you can essentially afford to apply less noise because, if you're summarizing a lot of data, you can afford to apply less noise because that summary, that aggregation step, actually removes information about individual people. But if you're querying one single data point, you need to apply a lot of noise so that it's meaningless to someone who looks at it. That's kind of the idea here. If you have thousands and thousands of things and you pull out a statistic that describes 1,000 out of 10,000, it should still be recognizable because that's what we want to do. We want to be able to use general large-scale information from this data. But if you look at any single data point, it's obfuscated and you can't actually see the details of it.
Thank you.
Yeah. So, let's see. Oh, this also helps data access kind of in that way, right? We can access data as long as we can be sure that we're not going to see any individual data point, that we can only see things globally, like that. So another idea, because the problem here, as we said, is that the incentive just isn't there. That this process, when you do it for the entire pipeline, really hurts the accuracy of the model to the point where it's unusable. So potentially we could use encryption to fix that. And by encryption, I'm going to refer to this as secure computation, because it's not necessarily encryption in the sense of taking a piece of information and encrypting it so that only the owner knows what it is. It's more like, yeah, we have to do that, but we then also have to be able to compute on that thing, that encrypted information. Otherwise, it's essentially useless from a machine learning perspective if we can't compute on it. So if we can do this, we can encrypt the data throughout this whole process. We can still solve this risk management problem because we can encrypt the data this whole time so that we don't have access to the data itself. We can actually fix this accuracy problem because what we're doing here is we're not adding noise in this process. We're literally just taking a computation that was done in plain text, encrypting it, and doing it in that encrypted space. It's the same exact computation with no additional noise added, but it's just done in a way such that the original inputs are invisible to the person doing the computation. This will make more sense as I go through the technologies and how they do it. So the problem here is that it doesn't solve model leakage. So we still do need something to take care of that, but it does solve the data access problem where we can have someone over here encrypt their data set and release it to us in an encrypted form, and now they can be confident because of these cryptographic guarantees that the data is not going to be essentially, it's going to be useless unless they follow the protocol that performs the machine learning on the data. So, and this will make more sense again as I go on. So what we end up doing, what we want to actually do here, is to take a hybrid approach where because the encrypted data and the secure computation approach, this one, because it takes care of the accuracy, we want to use that in combination with differential privacy. So then the leakage that wasn't solved can be solved with differential privacy, but we can also have the accuracy that we would expect from like a normal plain text situation. I keep saying plain text, what I just mean there is like a normal unencrypted value. And then in the future I'll refer to ciphertext as a private value. That one that can't be, if I see the ciphertext of a value, I can't actually know what the plain text version of that was. It's the encrypted value. Yep.
So what is being sanitized then? If the model still gives good results, then somehow the one that gets leaked is bad. How's that work?
So what's sanitized is the prediction. I didn't explain this too well, but when you have a model just being, let's say you train a plain text model on data that you had. You never release the data, you never release the model itself even. And people start sending you data to run predictions on it. If you serve those predictions, if you take them, take the data, run it through your model, take the prediction that comes out and send it back to them, that can, just that alone, even though it's essentially a black box to their point, they can still, that can still leak data or leak information about your model and or its training data to the person who you're serving to. There's what's known as a set membership attack, or membership inference attack rather, where if you give me enough predictions, I can use those predictions to essentially train a model that does the same thing, and then I can test any new data point that I find in the wild. I can test it against my model and see if it was a member of the original training set, which means I've effectively figured out whose data was used to train this model. There's also things called model inversion, model inversion was part of that, where you you serve enough predictions, I can then train a model that copies your model's behavior, and now I effectively have a model with not the same exact weights, but the same decision boundary, which is functionally the same thing as just stealing your model. It's a model with the same performance characteristics, the same behavior at test time. So this is why this leakage is a problem. And so differential privacy allows us to train a model in such a way where we have strict mathematical guarantees that won't happen, that information can't leak out of the model if I'm serving predictions with it. And a lot of these differential privacy mechanisms actually have a budget, so that once you exhaust that budget, you have to go and retrain the model, because at that point you're then starting to leak information again. So this is, differential privacy was like not necessarily the topic of this talk, but it's super interesting subject. There's a lot of people thinking about it right now. And, it's definitely more on the like machine learning, probabilistic, theoretical side, as opposed to encryption, which is more like I think people are more familiar with encryption because it's used in communications and storage already. But this is different encryption, which we'll go through next. But the point here is that privacy mitigates these bottlenecks. So then, how are we going to do this? By computing on encrypted data. So how does that work? So we're going to start off like the simplest machine learning example we can, which is prediction with a linear model. So just linear regression. For this specific example, on plain text data. User sends data. I, the model owner, have a set of weights. I perform a dot product on that data and send the dot product back. This is what that is mathematically. You take these two vectors, you do the dot product, and then you send the result, which is just the sum of the element-wise multiplication of the two vectors. So how we would do that with secure computation, I'll be talking about two techniques, homomorphic encryption and secret sharing. So homomorphic encryption is perhaps the more familiar one to our original notions of encryption. You have data, and the user secures it with a private key. They hold on to that key, and then they also send a public key to the model owner. So then they send this encrypted version of X, and the goal of the model owner is to return an encrypted version of the dot product itself, while only using the encrypted version of X and never decrypting it, because they can't decrypt it without the key that the user doesn't give up. So you have these weights that are in plain text, and you have these encrypted data points. So what we need is a public multiplication. That's what we'll call this. It's essentially, we want to take this encrypted value and multiply it with what's called just a plain text weight. That public multiplication will then move in that plain text value into the ciphertext. So the result of that, encrypted X times plain text W, will be an encrypted version of X times W. And then what we'll need is private addition, adding two encrypted numbers so that the result is the encryption of those two numbers added together. So this will give us, that formula at the bottom is actually this one right here, encryption of dot XW. So if we have these two operations, then we can perform a linear regression prediction on encrypted data. So getting those two operations, we need to provide something called a homomorphic encryption scheme. And we actually need something called probabilistic encryption to do this. So encryption, sorry. Yeah.
Yeah, in that previous slide, it listed public multiplication and private addition.
Mm-hmm.
How are you doing multiplication on one number that's encrypted?
So we'll go through it. We'll show an example. But first I want to talk about the actual encryption itself. Encryption in normal, I guess, cryptography, right, is taking something and just garbling it up in a deterministic way, such that I'm the only one who knows how I garbled it up, and then I can send it, and no one knows how I garbled it up, so they can't read it. If they had a strong enough computer, they could go through all the different possibilities, all the different ways of garbling to figure out, and then check each one to say, oh, all right, finally I landed on this one, and it's a sensible, message, so this must be it. Which is the problem here. If I send an encryption of 0 and 1 in just that kind of way, where I just garble it up, just switch the two, it's very easy for someone to brute force that, right? So we need what's known as probabilistic encryption, where for each plaintext value, there's a number of possible ciphertext values. So essentially what happens is this set of numbers in the plaintext is going to get much, much larger in the ciphertext, the set of possible numbers that each one could be. How that happens is, this is called a Paillier homomorphic encryption scheme. It takes in this input x, which is what we want to encrypt, plus some randomness r, that's going to be just any random value, essentially, just to remove, just so that there's missing information in this encryption to the, I guess, other person's, from the other person's perspective. And then this G and N is going to be a public encryption key, and the R is going to be essentially our private encryption key. So these are going to be integers. This mod means that we're doing this over integers. So essentially how we do this is with a fixed point representation of floating points. I'm not going to go too much into that, but it's essentially just to say that we take a floating point number, multiply it so that most of it is in integer space, and then make it into an integer, and we use that, which is going to also inform why this stuff is actually extremely computationally intensive. So these public encryption keys, let's just say they're public. We have 36 and 35. G is 36, N is 35, N squared is whatever that is. So if we have randomness 2 and a value 5 that we want to encrypt with that, we can perform this calculation. We end up with 718. Now we can do the same thing except with randomness 4, so a different private key, and the resulting number is 674. So these are two different encrypted values referring to the same underlying plaintext value. So the problem here is that these numbers are typically very large. They can be 4,000 bits as opposed to normal 32 or 64 bit numbers that we do normal computation on. So the computation becomes significantly more expensive. So private addition, how do we do that? We're actually going to take these encrypted versions, these encrypted numbers, using this formula, and then multiply them together to get a private addition. So if we expand this, we do that, basically just using properties of modular arithmetic, we can get to this expression, so that you can see actually that this is the formula for just the encryption of x plus y. So essentially what we're doing here is just taking these two values and moving them together, so that because of the multiplication, we can just then take the exponent of these two terms, add it together, and we end up with randomness r times s, which is still random, and it's a private key. And that's then the key that you would use to decrypt this encrypted value. So essentially, yeah, we're just taking these two inputs and adding them together, but we're doing it in an encrypted way. And so this is a concrete example where we took those two values before. 718 times 674 is 57. which is actually the same thing as 36 to the 10 times 8 to the 35 mod 35 squared or whatever, which ends up being that encryption of those two numbers added together, 5 plus 5. So to do public multiplication, you would do, essentially you would just add up a value w times. So we're going to basically just do this, w times, with the value itself. So that means taking it to the power of w, which then it's essentially the same idea. You can move it in, and then you end up with the encryption of x times w, which was a public multiplication. So these were the two things that we needed, and again, this is like a concrete example of it, where 5 times 2, you can do this, end up with an encoding of 10. So that is like not, it's not very intuitive, right? Cryptography is not necessarily intuitive when you go at this level, but it does work, and the math behind it is well founded, and it uses number theory and abstract algebra essentially to do this stuff, to prove that it works. So now if we want to switch this to secret sharing, it's quite a bit different. There's no longer any notion of a private key or public key. Instead, what happens is we're going to split the values to two parties. And those two parties, there's going to still be an encryption, but the encryption is no longer homomorphic in the sense that it won't preserve the operations in the same way. We can't like write out those equations that we just saw. So we have to kind of do something different, and that involves often involves communication between these two parties and exchanging values in such a way where you don't leak anything about the original data, but you also can be lighter on the encryption. You don't need like 4,000 bits, for example, as we needed before in that private key, or no, public key. Sorry. So how this is done is this person on the right is going to secret share their value, and they're going to send it to these two servers now, which in concert will compute the dot product. They'll usually do some kind of communication together to do this. They'll do it in concert, and then they will return the shares of the dot product. And these shares are specially constructed so that when you split them out and you only have one of them, you can't tell anything about the original data. But if you had both of them, you can reconstruct them to get the original data. So essentially, this person on the right splits their data into two shares, and these two servers, if they were to unite the values, they would be able to reconstruct the original data. But because there's this barrier, this I guess assumption that they won't collude, they can still do the computation in a way without revealing those values to each other, send the result back, and the person at the end can reconstruct the data itself. In this case, the dot product of x with the weights w that were already on the servers. So what we end up needing is essentially the same thing as we did with homomorphic encryption, but we're going to call it homomorphic secret sharing instead. We still need this public multiplication and private addition to do this. So how do we do that in secret sharing? So this is actually how we share values. So you have this x, and again we have some randomness r. Share 1 is just going to be the randomness modulo some m number. And then share 2 is going to be the original value subtracted by this randomness modulo that m. So what ends up happening here is that because r is random, the value of x is only known by the person who did this process. And then share 1 and share 2 look like randomness to anyone who doesn't have x. And it's set up so that if you add up those shares together, the r's cancel out, and then you just get some x. This I think is a little bit better than homomorphic encryption. And like if you look at the literature, it's definitely apparent. So for a concrete example, let's say we take randomness 7 and create two shares of it. So 5 and 7. The first share will be 7 mod 10, which is just 7. The second one will be 5 minus 7, which is negative 2 mod 10, which is 8 in modular arithmetic. And then when you add those together, you get 7 plus 8, which is 15 mod 10 is 5. Yeah. So this essentially just proves that if we secret share these values, we can reconstruct them. So then we have to then have private addition, public multiplication. So with private addition, we essentially want to add x and y. X is these two, x1 and x2 are each shares of x. Well, same with y1 and y2. So we have these two shares, they're on different devices, and we want to compute x plus y, which is essentially x1 plus x2 plus y1 plus y2. But we don't want to exchange those numbers. So how we do that is actually just by adding up the values on each server. So we take x1 plus y1, and that will give us z1, and then we take x2 plus y2, and that will give us z2. And so then if you look down on the bottom right, if you wanted to compute x plus y, what you could do is just add those up, and this relies on the fact that addition is, you can change the order. We end up with something that represents z1 plus z2, which is just z, which is x plus y. So if at the end of this, they were to send those shares to each other and reconstruct them, they would end up with z, which is the result of adding the original values. But they did that without revealing to each other what x was and what y was. In fact, they didn't even have to see what x and y were because someone else could have secret shared x and y with them. So doing this with public multiplication is actually somewhat similar. You can essentially just multiply w to the share. So if you had an x secret shared between two servers and a public value w that both of them knew, you could multiply that w onto the shares themselves, and then if you were to reconstruct them, you'll end up with essentially z1 plus z2, which is x times w in this case. So that essentially is all you need to do to be able to perform like basic machine learning with at least predictions on a machine learning model with public weights. Yeah.
I think I can see how that could hide weights. Is there some way that would also hide the structure of connections?
So it doesn't. Yeah, it doesn't hide the structure of the connections, but it hides the values of the connections themselves, like in a neural network. And actually, in this case, it doesn't. In all the cases we've gone through so far, it doesn't hide the values of the weights. The weights are assumed to be public. You need one extra thing, private multiplication, to be able to do hiding the model, which is what comes up next. But yeah, in general, for general private deep learning, you need to share the architecture itself, like the shapes of all the tensors that you're multiplying together or that you're using in your architecture. And you also need to be able to share which operations are going to be done on all that data. But the values that you use in that graph, in that computation graph, those can be masked. And when we think of both security and privacy of models, that's actually what, without those weights, I'm essentially saying I'm using this architecture, but you don't know how to get that architecture, right? Necessarily. Like if you don't have the data, there's no way you can train that model, for example. But if you don't need data, if I share my weights with you, you no longer need the data to retrain the model. You just have the model. Okay, so using secret sharing with a private model, instead of having these just W's on the servers, these public values, W, we can have those secret shared beforehand, such that then we can do this without revealing the weights themselves. So now what we need is a private multiplication. And I'm actually not going to go through this. It's like way more intense. Yeah, but it's I guess the only addition is that before we were able to do private addition and public multiplication without really sending material back and forth. In this case, we end up needing to do that. We use these things called triples, and the way we end up computing x times y is by computing those values all the way on the right, z1 and z2, and then adding them together if we want to reconstruct it. But to compute z1, this server 2 has to send some information over to server 1 and vice versa, which creates a communication cost. So like a key highlight here is that homomorphic encryption, we said those values can be as large as 4,000 bits, which makes computing on them extremely intense. But the networking is super easy, right? They can just send encrypted data, so sending 4,000 bits as opposed to 64 bits, like isn't that bad. And you're only doing it one time, especially, that's what doesn't make it bad. But here, every time we want to do a multiplication, we have to send material between servers, which gets really costly in terms of networking and communication. So the trade-off is that homomorphic encryption can be slow compute-wise, but fast networking-wise, whereas secret sharing can be very fast computationally, but slow networking-wise. So for example, if you had a server and I had a mobile phone, we probably wouldn't want to do secret sharing together because the communication between those two devices is going to be a really long time, and it's better probably to set it up so that the computation is what takes long. Like if I'm a mobile phone owner, I can just construct this homomorphically encrypted value, send it to the server, and then if that's in the cloud, you can just beef that server up so that it runs quickly enough. Whereas with secret sharing, if you're already in the cloud, if you already have every party in the cloud, it doesn't make as much sense to do homomorphic encryption because you have extremely fast networking between all those devices. So you can do secret sharing, and it's going to be a lot faster than homomorphic encryption would be, at least so far. There's also other problems, but anyways. I guess the point I'm trying to make here with all of this is not necessarily to teach you cryptography. It's just to demonstrate that this is like a problem that isn't just cryptography. It's cryptography, yes. You need these techniques, these protocols, in order to essentially solve this trust problem between the different parties in machine learning. But then also you need machine learning, right? So when you scale this up past linear regression, the types of model you use are important. You can potentially approximate things in your model to make things faster. Because we used integers instead of floating points, we need to worry about precision. Precision matters and has a definite impact on performance. But these are all things that the machine learning community is already working on. So we need essentially this challenge is that we have these different fields, cryptography and machine learning, and some other fields that don't necessarily work together now, but we need them to have a common place to work together if we're going to make progress on this problem. Engineering, of course, is another one. Secret sharing is a distributed computation problem. And we want to be able to run this stuff on multi-core architectures, whether it's a CPU, a GPU, whatever other device that you want to run this on, like a mobile phone, and whatever processor they have. But then it's incredibly important for this, it's a software engineering challenge because it's incredibly important for the code to be readable so that someone can look at the system and it's auditable so that all these moving parts, they can say that security and privacy isn't broken anywhere. But then it also introduces a lot of challenges around the data science workflow in general, outside of machine learning. Because machine learning is one part of a long list of things you need to do to be able to do data science in a productive way. So for example, data science, we need to rethink use cases and how we approach them. And it also is challenging for the data scientists wanting to work with these technologies because things that you take for granted, like being able to clean your data, how do you do that if the data is encrypted and you can't see it? Right? It's a lot harder. It's not necessarily impossible, but it's not straightforward at all. And then things that also were pretty easy before, like monitoring a machine learning model for data drift or something like this, or model drift rather, that's also not as clear anymore. Once we get in the situation where you don't see the predictions that you serve, how can you be sure that your model isn't drifting and it's still performing well? Still, I think a solvable problem, just not clear how. It's not easy, and it probably requires additional technologies beyond this in order to be able to do it. But the bottom line is that they need a common language, and that's what we're working on. Ta-da. TF Encrypted, making it accessible to ideally all these different audiences, so that they all have a place to work without necessarily stepping on each other's toes or having to reproduce what the other person does. So TensorFlow, if you don't know about it, is a platform for machine learning development and deployment. It's very popular. It was developed internally at Google. It's actually originally created at Microsoft under the term NIAD, but Microsoft didn't really do anything with it, and then it moved to Google, and Google essentially picked up the engineers who worked on it, and they developed the precursor of what's now TensorFlow in-house. But it's the most popular machine learning framework by paper citations, industry usage, etc. And here's how we use it. So this is a diagram essentially representing the architecture of TF Encrypted. So it's built on ordinary TensorFlow, and it doesn't completely disguise it, so you can still use TensorFlow the way you normally would, which is kind of important when you think of how slow this stuff could be, this privacy-preserving machine learning. You want to move things potentially progressively into the encrypted space. You don't necessarily want to encrypt your entire thing. You just want maybe encrypt enough where it works for the use case. And so it's important to be able to write programs that rely on both plain text and private technology. And this is also useful because we get to take care of, TensorFlow has a really highly optimized distributed computation engine behind it, and it also has like an extremely efficient tensor computation implementation, linear algebra package essentially, and then it also has the higher level machine learning layers built on top of it, which are necessary to be able to do machine learning reliably and reproducibly.
Would this stop someone from brute forcing a model to reverse engineer it?
That's what differential privacy would help with. But no, I guess by brute forcing a model, you mean like I have an app, there's a model behind it, it's a black box, I can just query it a bunch of times and then create enough training data to create my own model?
Right.
No, so at least to get a model of the same performance, if you added differential privacy, this was one of the earlier slides where we talked about combining like a hybrid approach between the encryption and differential privacy. If you had that, yes, but it wouldn't completely take away your ability to brute force a model. It would just ensure that the model you got was slightly worse than the model that I have. And I think that's generally the case. There's not really a good way of doing that. There is a paper from DeepMind called shared model governance via model splitting. So MPC can be seen as a way of doing shared model governance where multiple people own the model, at least until the model, once it's trained, is reconstructed. It remains in the shared state between parties, which means that without the other party's cooperation, no one can use it, which effectively means that it's governed by everyone in that group. So what they've, and so this is shared model governance. It's an interesting idea, especially if you are thinking about like long-term safety. There are like long-term issues around AI, like governance, things like this. So what they did was they said, like that's a pretty good way of doing it because no one has any idea what any of the values in the model are. So if anyone wants to steal the model, they essentially have to train it from scratch. But what this paper did was it looked at if you, instead of encrypting the stuff and doing like multi-party computation, which is slow, if you just split the model layers, like in a deep learning model, like if you, let's say I take every other layer and you take every other layer, how long will it take either of us to train up to the original model's performance? Especially if we're allowed to do things like add multiple layers where you only have one layer to try to like pick up like performance that I'm losing, I guess, by not knowing your values. And they basically create this like hardness metric of model theft around this stuff, which is, it's interesting. The threat model was, I think, a little bit underdeveloped, and they explicitly say that in the paper. Like we're not really trying to, like with MPC, the threat model is very well developed. It's less developed here, so it's not clear if like if the results of that paper are realistic. If someone were to actually do this at like a large scale and in a way that would try to prevent something like that. But it's a super cool idea, and I think it's a cool paper to like think about if you're interested in this kind of stuff. Yeah. Anyways, the architecture of TF Encrypted. So we have ordinary TensorFlow. So the idea is that you can, like I said, easily mix ordinary and encrypted computations in your application. This can be your program, which trains your model, or it can be like your downstream application that uses that model once it's trained. So then what we've done in TF Encrypted is built secure computation protocols, like the one you saw with secret sharing, directly into TensorFlow, which again means that we can we can use the distributed computation engine as well as the tensor implementation that they have in order to be able to do this in an efficient way. And it is very efficient. As far as our numbers go, we match or beat state-of-the-art papers that have been published in this subject. And then we also provide standard operations in their encrypted form. So all the tensor operations in normal TensorFlow, we basically reproduce them in an encrypted way. So this includes matrix multiplication, convolution, pooling layers, activation functions, all this stuff that you would expect from like a deep learning library. Some of them are exact, like exactly the same as you would see in plain text. Some of them have to be approximated, but we have most of the ones that you'd care about coming from, a deep learning background. And then what we also want to eventually have, which we don't have yet, is there are a lot of third-party libraries from academic groups working on secure computation that are pretty optimized and have like a long history behind them. And these groups are working on improving the cryptography behind this stuff. So we don't necessarily want to reinvent that or have to reproduce it in TensorFlow every time. If it's more optimized, like our MPC version is, then it makes sense to do that. But a lot of times we want to be able to use these third-party libraries so that the cryptographers can handle the cryptography while we focus on creating this framework that lots of different people can use without needing to worry about cryptography. Okay, so now, let's see, wow. Okay. There's a lot of use cases here. Basically, different ways you can do prediction and training under this setting. I guess I'll go through some. There's code examples. If there's anything between, prediction and training that you care more about, I can focus on those just in case time is an issue. But if not, I guess I'll just go right ahead and we'll see how it goes. So for prediction, if we wanted to run a prediction on a model, we have the model weights on the left. So this could be, now we've moved beyond linear regression or logistic regression. We want to do general deep learning. All of this will fit now. So how this works for prediction is the model owner will essentially, we have the model owner, the data owner, and then these two compute humpers. And it should be noted that these people can actually be the compute humpers themselves. They can do this stuff together. But it's just helpful to think of, because it's more optimized, and it's, I think, helpful to think of these all as different, distinct parties. So it's important to note that these two servers will never learn enough information to reconstruct the weights and the data individually. So as long as we can trust that they won't collude, this will be privacy preserving, provably. So you share the model weights, and by privacy preserving, again, I mean the values of the weights can never be uncovered, and the value of the data can never be uncovered. The shape of it can, it needs to be known in order for this to be able to be done. And the function that you're running on it, which is the model architecture that you're using to run the prediction, that has to be known to everyone. Otherwise, you can't, they won't know what to compute, essentially. But if they know those things, they can follow a protocol that will allow them to compute the prediction without the weights being known or the data input being known. Anyways, secret sharing, they're going to compute together in a way that we saw with the previous slides. And then the logits, which is essentially the prediction, those will be sent back to the data owner. This essentially represents their prediction. And so this is now data about them that they can reconstruct and then use in the application. So doing this with TF Encrypted, how this is different from TensorFlow. So on the left, we have something, a TensorFlow script that does this exact process. It's going to need to provide weights, essentially load them from disk, provide input, which is taking the data from disk and pre-processing it, and then a receive output function, which is essentially just going to print the prediction. It's going to take the logits, do the argmax, which tells you which class, this is classification. So you it'll take the maximum logit, which is the same thing as taking the best guess of the class. And it's just going to print that on screen. Here we're going to call these functions. First we load the model and the input. We construct a neural network, kind of how we would in lower level TensorFlow. This is a simple, I guess, 3-layer neural network with ReLU activation functions. And then once you get the output, which is the logit, you run it through this prediction op, which is the receive output, which is essentially just going to print out the prediction. And then this is a normal TensorFlow session. I guess in TensorFlow 2 they're moving beyond this. They're no longer going to be using this TensorFlow session for pretty, I guess, technical reasons about like compile time versus like static versus dynamic computation graphs, which is like what these deep learning frameworks implement. TensorFlow was a static graph for a long time. PyTorch, which is new or newer, is dynamic. Now they're both doing what the other person did and adding both so that you have both of these paradigms in the same framework. But essentially a session is an artifact of the fact that we're compiling a model first with all of this stuff, and then we're eventually going to run that compiled program. And so yeah, so this is how you would do a normal TensorFlow script, at least in TensorFlow 1.x. With TF Encrypted, it's very similar. You import TF Encrypted alongside TensorFlow, meaning you could still use both of them. Now, instead of executing these functions that we defined on our device, we're going to wrap them in this handler, which we need to annotate with who is responsible for running that function. So in this case, providing weights is the job of the model owner. So we feed that function and annotate it with the model owner, saying the model owner needs to run this. And then it returns these weights. But these weights are actually private tensors, so they're going to be secret shared tensors that actually represent two different shares on different devices. From the user's perspective, it's just one tensor, and it's essentially the same, but behind the scenes, a lot's going on to make sure that this is done privately. Yep.
What is a tensor? Is it one tensor?
Tensor, you can think of it as a piece of data, but a generalized version of that. So like it's just a number. So you have, it's essentially an array, but it's a multi-dimensional array. If that helps. Okay, so you could have a number, or you could have a list, an array,
Okay.
which is a single-dimensional array. That's also known as a vector.
Okay.
You can then have two-dimensional array, which is a matrix, or you could have a three-dimensional. So you can imagine an n-dimensional array. That's what a tensor is. It's a generalization of a matrix or a vector or just a number, but it allows you to think about them and like organize them, I guess, together. Yeah. And there's a long history of this stuff behind, like in math. Linear algebra is a subject that talks about using these in a way for mathematics and what the implications of doing that are. That's like definitely like a strong underpinning of modern machine learning is that concept. So again, if we want to use these other functions, we are going to annotate them the same way, but because these two functions provide input and receive output, are delegated to a prediction client because it's their data, we are going to annotate them with their name. Really, these names can be pointing to IP addresses that represent devices. So this prediction client can be, like how we actually do this is a model owner can be like my device, like my computer. Prediction client can be like someone else, someone's phone. They both have IP addresses. They're provided in like a config that's not shown here. And then also under the hood, TF Encrypted is running a protocol, and that protocol also points to specific devices. So those devices can also be the same IPs as my device and the other person's, or it can be two cloud servers that are going to do the computation on our behalf. But either way, the servers that you shared or that you provided the protocol aren't going to see any of the information from the other devices, from these two devices. Because those functions get run on the device that they're annotated with, basically, and what else? What the rest of what this function is wrapping up is the encryption part, where it actually encrypts on their device, and then it sends it to the devices that are designated by the protocol behind it. But we wrap it up in a way that it feels like pretty close to normal TensorFlow, or at least lower level TensorFlow. So this is a picture of a TensorFlow computation graph. It is colored by device. So you can see that what we defined here as the output and the input to the model are owned by this one color, which is the prediction client's color. This is the weights. These are the weights of the model. That was provided by the model owner. It's a different color than this, signifying that it came from a different device. Then you have these three colors, which are all the compute servers that the config that I said was hidden away. Those are the compute servers defined by that config. And so you can see this as essentially just the graph of what we do when we do a logistic regression model. So we take the input, run it through a matmul. That's a bias add. This is a multiplication. Why is that a multiplication? I'm not sure why it's there. But then you run it through a sigmoid to get the probability score of like, the classification. This is actually more than. Yeah, I don't think this is actually a model. I think this is just like a plain script. But essentially, you can see that you're building up like layer by layer. You're running this through. You could run this through a neural network in the same way and like examine it this way. And what's nice about this is that you can then click in on each of these squares and make sure that data isn't being leaked to a wrong party. So you don't even need to necessarily read the code to verify that a computation was run successfully and securely, which means auditing is like a lot easier. And also you can color these by how long each operation took, stuff like this. Whoops, TensorFlow is nice that way. There's like a lot of tooling that we can take advantage of in this situation. And this is just to say, if we expand the input and output, so the data input on the left and the model output on the right, these are all happening on device, on that prediction client device. We're actually using like a TF data pipeline to pre-process the data. And then this is where encoding into the integer from like a floating point number to an integer happens. And then from there, share and local mask, those are two operations that actually encrypt it. And then you can see the result of those just getting sent out of this operation. And then if you look back, this is where they get sent out. And then they're encrypted already, so they get sent to this multiplication, this matrix multiplication, which is done securely. Okay, so that's kind of how that works. Some other use cases are joint prediction, which is basically just doing the same thing, but where different people provide different features about a single person. So we can do this just by having each device share their own piece of data and concatenating them together into a single point and then running it through the same thing that we just saw. And then we get the result. And those shares can be sent to whoever is designated as the person to get that result. So the code is very similar, but we're going to just create functions that provide each different feature, annotate them with the feature owner's device, and then concatenate them together and run it through the model. In this case, it's just a normal, like linear regression. And then the result receiver could be one of them, it could be someone else, but it's also another device that gets annotated as the person who receives the output. Yeah, basically what I just said. Training, which is probably more interesting. Sorry, did you have a question?
Yeah, I had a more general question. Is now a good time to?
Maybe we'll hold it to see if there's, I mean, unless, I don't know, I could do either.
Is this like the last section?
Yeah.
Yeah, I'd say we'll hold that as a general wrap up then.
Okay. Cool. So training, we want to be able to do is train a machine learning model without seeing the data. It's going to be very similar. A doctor or someone is going to share a data set The compute helpers are gonna work on it, and then what is gonna come out is, so the weights have been initialized as private values on device, or actually they can be public values because they're initialized that way. So the compute helpers can then do the computation and then send out the resulting model. So it can either be, in this case it's private, the weights can be public or private depending on what you want, and public is much faster. So this is just to say that the compute helper can be replaced by a doctor. So the doctor himself, one of the data owner can be one of these people, the model owner, and the model owner can be one server, the data owner can be another if you want, or it can be, the data owner can offload that computation to another server. And this is what I was saying before with shared model governance. This model can be sent to some other location and then reconstructed, like here, or it can be sent in its original state, and then that model is then shared, it's still shared, and it can be used for private prediction like before, the examples that we just ran through, which means that it can be co-owned between these two servers that are doing that. So this is how you do private training. This is a logistic regression model. You define it. So this is a high-level API that's like definitely not set in stone. It was kind of made for demo purposes, but essentially like the same thing that you would normally do happens. You define like your forward pass, your backwards pass. So we don't yet have autograd, so you have to define your own backwards pass, which is going to be changing in the next like month, I would say, hopefully. But essentially, you can create this model, designate data owner and model owner, and then create the inputs based on who owns the data, define the weights, like who's going to receive the weights afterwards, designate that as the model owner, and then run a model.fit, which is like similar to Keras style, just like training the model, and then evaluate on test data if you need to, or which you probably did. This is how it looks. It's very similar. Sorry. Data owner defines their inputs. The inputs either go into training or evaluation. This is where the actual weights are created and initialized. This actually trains the model. And then once you're done, the weights themselves, which are here, these are the secret shared weights, they get sent to the model owner who reconstructs them on their device. So you train the model and then get it out at the end. Yep.
So does this require twice as much computation when you do these secret share and your ones all in the leg and ones the real data minus the millers?
At least.
Everything twice?
At least, yeah. Usually more. So it becomes more costly. Yeah, performance is definitely an interesting conversation. Maybe we'll hold it, but it's so that like here you do a few times more computation, but really that's not the problem because you can throw, so like more compute at it, and you can get it to run as fast if you're willing to spend the money. The problem is that the communication is what really slows you down. You have to communicate between the servers. So if it's done in a cloud, in a single data center or something like this, you can have high bandwidth connections. Then that's fine, and it's like a good one to use, but otherwise it becomes really slow, not even because of the compute, because of the networking. Joint training, so what's really interesting is that you can take data from different sources and combine it and then train it on that. So you have two different parties who own data, that's essentially like private, that people are willing to share together. Like maybe this is multiple hospitals, and under HIPAA they can't share the data, at least without going through a lot of extra steps. They can share, secret share their data, compute it together, come out with a model. It's pretty easy to express. It's the same way. You just have multiple data owners. You define multiple data sets and then concatenate them together to do that. You can also do federated learning. We actually haven't talked about this until now. Federated learning is also known as on-device learning. Essentially the situation where I said, I can just send my model to you and you can do it. I don't need your data from it. What's nice about this is that you don't need as much of this encryption stuff to keep the data private. What's bad about it is that the model, then you're giving your model to basically everyone, or at least someone has the final model, right? That's not you, and that could be a liability. But if you want to keep the data decentralized like that and you want to train the model in that way, what happens here is you have your weights, you send them to all the participants, they run the model on their local data. So this is basically how this works is you send them the weights, they run an update step, everyone does this locally and then sends their result, their model update back to the server. The server aggregates those updates and then that's the new model. And then once they have a new model, every so often they broadcast that version of the model to the same people. And you do this over and over and you can learn from data that's distributed in this way without collecting the data. But the problem there is that these updates, once they're done on device, once you send them to the server before the aggregation, you can actually use those updates to reconstruct the original data. So you actually don't get like really strong security of this data because the data, the gradients for the updates, the model updates that you create are just being sent to that server, and with a little bit of extra computation, they can then just reconstruct the data, which then leads you to ask like why even do this, because like you're not actually providing privacy if Google can afford to just do that extra step of computation to do that. The trust is still there. You still need to trust that they're not going to do anything bad with that data, or that it's not going to leak. What you can do is do the aggregation step securely. So they create the update, they secret share their update and send it up to that server. Instead of one server, it's now two servers. And then they can do secure aggregation using multi-party computation, which is essentially just averaging these updates together the same way you would normally, but you do it securely so that possibility is just no longer possible. The possibility of reconstructing the original data. That's what that says. So this is how it looks in code. It's basically similar to the other code I showed. You just have multiple data owners. The one thing that's different is that when you provide the input to TF Encrypted, it actually takes the form, it's the output of this compute gradient function, which is actually a full forward and backwards pass on a model locally, which is different than any of the other examples that we've run through. And then what you do with the output of that, the gradient, you aggregate them in this way. You add them up in a secure way using TF Encrypted. And then you can, essentially this is what you see, where you have the parameters initialized, you broadcast them to the different parties, they each run the model, so this private input is actually a full run of the model, and then it produces like the update that they would make to the model to make it better. You secret share those and send them to this server where the secure aggregation is done, and then you send that out to here, which is then the final model. And then they can send that back here to start the process over to train the model, essentially, to keep the training going. And then once they're done, that output cell just has the final model that you wanted to begin with. Yeah, and this is an example of where TensorFlow does some optimizations under the hood because it recognizes that this is like a repeatable computation and that there are all these tricks that they've programmed into TensorFlow that make it run extremely quickly, and it helps, is essentially the bottom line. Roadmap, as you can see from the code, it's still pretty low level. So TensorFlow 2.0 is standardizing around Keras, so we're going to do the same thing. We're actually doing that right now. That's what I was doing today. Keras is a higher level library used for training neural networks, which is much easier to use than like the lower level tensor computation stuff. It's like much more intuitive based on how you would expect to build models layer by layer, as opposed to with like basic addition, multiplication, stuff like that. But this also allows us to do things like provide pre-trained models. One thing that we didn't really cover so much is that specific operations in the model can make it really slow. So if you're not aware of what operations are slow, you could just take your model that you expect to work and run it securely, and it takes forever. And it's because the specific operations you used are not optimized in the secure space as much as they are normally. For example, ReLU is way slower in encrypted space than it is because the comparison is like a hard thing to compute. Because so far we've talked about like addition and multiplication, but not how you do like comparison, which is like a very important thing. So you can actually approximate that stuff to make it faster, but if someone doesn't know that, they're going to have a tough time. So providing pre-trained models, you can kind of allow for that, skipping that whole problem. Yeah. And then ideally, we want tighter integration. There's like a lot of projects in TensorFlow around privacy that we didn't really cover. So like there's the normal TensorFlow ecosystem, like TensorFlow Data and TensorFlow data sets, and like all these libraries to help like the processing of your data before it gets to the model. And then TensorFlow 2.0 is like a much easier way of using TensorFlow for machine learning. So right now we're on TensorFlow 1.x, we want to move to 2. And then TensorFlow Privacy is for doing differential privacy in TensorFlow. And TensorFlow Federated is a particular library for federated learning. So ideally, we would like to unify ourselves with these libraries, or at least make ourselves compatible. And these are being like developed by the brain team, so it does make sense for this all to happen together. Yeah, like we said before, third-party cryptographic libraries, that would be nice to have, because then we can let the cryptographers focus on the cryptography and focus ourselves on making this usable. And then we want to improve the performance always. We have a lot of ways to do that we haven't gotten to because we're building the software. But I mean, the idea is that the software is actually like a really strong way of doing this stuff and doing not only research, but doing it in production as well. So, I mean, right now it's targeted towards researchers, but the goal is to have it so that if you wanted to build on top of it to have it be production ready, you could. And we will. Anyways, to wrap it up, what's cool about this is you can compute on encrypted data without having the ability to decrypt it while it's being computed. What that allows us to do is mitigate bottlenecks in the existing data science process and enable access to sensitive information that is useful for providing innovative applications of AI. Secure computation distributes trust and control, which is cool because it allows for different ways of thinking about like the usual way of doing machine learning. And it's complementary to other approaches that are also necessary in order to get this whole picture running. And then privacy-preserved machine learning is a multidisciplinary field, requires adaptations for everyone, and it also requires a common library that's usable and integrates them all together. We're hoping TF Encrypted will be that. That's the GitHub. Our company put out this other thing called TF Trusted using something we didn't talk about called Secure Enclaves, but it recently won the Google Cloud Confidential Computing Challenge. And it's like a totally different way of thinking about this stuff. It's hardware-based instead of cryptographic, but it's definitely like an interesting area if you're interested in this whole topic. It's called Secure Enclaves, and we have an example of doing TensorFlow in one of those enclaves up at that link. And just some context stuff, but you all know that, so. That's it. And there's more. No.